Hi, good morning. Today we are going to start our next module, module 2. In this is also a continuation of our sixth chapter, starting with 6.3. Order in the space of self-adjoint operator. So in this case, we are discussing about only self-adjoint operator, that is symmetric operator. And what is about order? Like you already know how to define an order relation in real numbers, etc. Like that, we are defining an order in the space of self-adjoint operator. Clear? So now moving to definition, an operator A is called non-negative and we write A greater than or equal to 0 if and only if inner product AXX greater than or equal to 0 for all x belongs to H. Okay, so we are defining an order relation. Okay, an operator A is called non-negative and we write A greater than or equal to 0 if and only if inner product AXX greater than or equal to 0 for all x belongs to H. And using this property, we are defining A less than or equal to B means symmetric means both A and B are symmetric and B minus A greater than or equal to 0. If we are here we are discussing only about symmetric operator, and A less than or equal to B means both A and B are symmetric and B minus A greater than or equal to 0. What is the meaning of that? B minus A greater than or equal to 0. B minus A greater than or equal to 0 means inner product of B minus A x greater than or equal to 0. So if you look at our property 6.6, inner product AXX belongs to R for any x belongs to H if and only if A is symmetric. So here we now from this definition we have an operator A is non-negative implies inner product AXX greater than or equal to 0. Inner product AXX greater than or equal to 0 means it is clearly a real number. That means by 6.6 we have if this belongs to R, then if and only if A is symmetric. Okay. So from this we get if A is a non-negative operator, then A is symmetric. If A is a non-negative operator, then A is symmetric. Okay. So this is the order relation. Here we have A greater than or equal to 0 means inner product AXX greater than or equal to 0. A less than or equal to B means both A and B are symmetric and B minus A greater than or equal to 0. Okay. Now next moving to properties of ordering. The first property is minus I less than or equal to A less than or equal to I implies norm of A less than or equal to 1. Okay. Minus I less than or equal to A less than or equal to I implies norm of A less than or equal to 1. Okay, clear? So before going to the proof, we are discussing one result. Suppose there is no need to write this in your exam paper. Okay, you just write the result only. Suppose we have A less than or equal to B. What is the meaning of that? A is and B are both are symmetric and B minus A greater than or equal to 0. So the result is, suppose A less than or equal to B, then inner product AXX less than or equal to inner product BXX. What is the meaning of that? A less than or equal to B means B minus A greater than or equal to 0. That means inner product of B minus A x x greater than or equal to 0. That is Bx minus Ax x greater than or equal to 0. That means inner product Bxx minus inner product Axx greater than or equal to 0. That means inner product Bxx greater than or equal to inner product Axx. So A less than or equal to B implies inner product Axx less than or equal to inner product Bxx. So what we have given this, okay. So here minus I less than or equal to A. That means minus I x less than or equal to inner product AXX. And A less than or equal to I imply inner product AXX less than or equal to inner product IXX. But what is this one? This is same as Ix is same as this is minus Ix. We have uh, CAX is same as CX. So minus Ix is same as minus Ix, and Ix is minus X. Sorry, here minus sign and Ix is X. So this is minus X. So here we have minus x inner product axx and less than or equal to this one. And you can take minus outside, remaining is inner product xx, that's equal to norm of x square less than or equal to inner product axx less than or equal to norm of x square. Now this is true for every x belongs to H. Now if you consider for x not equal to 0, you can divide throughout by norm of x square. Thus we get minus 1 less than or equal to this one less than or equal to this one. And that means modulus of this less than or equal to 1. Norm of x square is always positive. Therefore, norm modulus of inner product axx divided by norm of x square less than or equal to 1 for every x such that x not equal to 0. That means this term is less than or equal to 1 for every x not equal to 0. That means supremum of x not equal to 0, modulus of inner product axx by norm of x square is less than or equal to 1. Okay, this implies norm of A is less than or equal to 1. Okay, this is the definition of norm. This implies norm of A is less than or equal to 1. Okay, that is our first property. Minus I less than or equal to A less than or equal to I implies norm of A less than or equal to 1. Okay. Now there is another note as a continuation of our first property. If A is a self-adjoint operator, then minus I into norm of A less than or equal to A less than or equal to I into norm of A. Okay. Once again, minus I norm of A less than or equal to A less than or equal to I into norm of A. We have defined if C equal to supremum x not equal to 0, inner product of ax by x norm of x square, then if A is a symmetric operator, then we have C equal to norm of A. So if A is a symmetric operator, then we have norm of A equal to supremum of this value. So A is symmetric implies supremum x not equal to 0, this equal to norm of A. This implies this is less than or equal to norm of A because supremum value equal to norm of A. That means and this is less than or equal to norm of A for every x belongs to H such that x not equal to 0. Now inner product AXX less than or equal to norm of A into norm of x square. Okay, and from this what we get, this is some number and no mod less than or equal to that number. That means minus norm of, this is of the form mod x less than or equal to c. That means minus c less than or equal to x less than or equal to c. So minus of this less than or equal to, okay. So minus a into inner product xx less than or equal to inner product, this is less than or equal, okay. And this you can write as inner product ix x, and this is less than or equal to this one. And norm of A is a number, you can take norm here, and this is like this. And from this you can write this as minus A into ix less than or equal to inner product axx less than or equal to norm of A into ixx. And the meaning of this is minus norm A into I less than or equal to A less than or equal to norm of A into I. And from this we get minus I A norm of A less than or equal to A less than or equal to I into norm of A. This is also from our first property. Okay. Now moving to next property. A greater than or equal to 0 and A less than or equal to 0 imply A equal to 0. Okay. Here we have to prove this in the case of operator. This is not the numbers. In the case of numbers, if we have x greater than or equal to 0, y less than or x less than or equal to 0 implies x equal to 0. Similar result also hold in the case of ordering operators. Okay. So we have A greater than or equal to 0. This implies inner product AXX greater than or equal to 0. Okay. Suppose A less than or equal to 0. What is the meaning of that? A less than or equal to 0. This implies you can write minus A greater than or equal to 0. That means, or you can write A greater than or equal to 0 implies inner product AXX greater than or equal to 0. Now A less than or equal to 0 means, what is the meaning of that? A less than or equal to 0. That means A less than or equal to B implies B minus A greater than or equal to 0. Okay. So here we are applying that result. A less than or equal to 0 implies 0 minus A is greater than or equal to 0. So that is what we are applying here. Okay. So this implies minus A greater than or equal to 0. Minus A greater than or equal to 0 means in a product of minus A of x, x greater than or equal to 0. That means minus, this is actually you can write one more minus AX, x greater than or equal to 0. That is minus inner product AXX greater than or equal to 0. That means inner product AXX less than or equal to 0. So there is no need to write all these things. You can write we have A less than or equal to 0 implies inner product AXX less than or equal to 0. And from 1 and 2 we get inner product AXX equal to 0 for every x belongs to H. Therefore, norm of A equal to supremum x not equal to 0 inner product of AXX divided by norm of x square is equal to 0. This implies norm of A equal to 0. And using proposition 6.155, okay, and this implies norm of A equal to 0, and norm of A equal to 0 implies we get A equal to 0. Okay, now moving to generalized Cauchy-Schwarz inequality. Just to recall what is Cauchy-Schwarz inequality. In the case of inner product space, let A greater than or equal to 0, then we have generalized Cauchy-Schwarz inequality as modulus of inner product of AXY less than or equal to root of inner product AXX into root of inner product AYY. So, just to recall what was our inner product. This was our inner product. Cauchy-Schwarz inequality. Modulus of inner product of xy less than or equal to inner product of xx all raised to 1 by 2 inner product of yy all raised to 1 by 2. This was our Cauchy-Schwarz inequality. Okay. So for proving this, we are proving one result, and that result is we have if inner product xy satisfies. This is one exercise problem in the second chapter. You can see this in page 26. If inner product xy satisfies all the three conditions of inner product except inner product xx may be 0 for a non-zero element, prove that Cauchy-Schwarz inequality is still true. If a inner product satisfies all these conditions except this, then that inner product we call as a quasi inner product, and we denote this as like this. So for quasi inner product of x and y, we denote this is we get this one, that is quasi inner product of xy. For quasi inner product also, Cauchy-Schwarz inequalities holds. That means inner product xy less than modulus of inner product xy quasi inner product xy less than or equal to quasi inner product of xxx whole raised to 1 by 2 into quasi inner product of y whole raised to 1 by 2. So we are using this result for proving here. Okay. So here we are denoting, let A be a symmetric operator, and we define quasi inner product xy as inner product axy. So now we are proving if we define this like this, okay, then this is a quasi inner product. Then it satisfies, clearly satisfies Cauchy-Schwarz inequality. So our first aim is to prove this is a quasi inner product. Okay, that means if we define this like inner product AXY, then this is a quasi inner product. So what about the first property of inner product? Quasi inner product satisfies all the property of inner product except the inner product xx equal to 0 implies x equal to 0. Okay. So first we have to prove the inner product xy, quasi inner product xy greater than 0. So consider uh, inner product xx greater than or equal to 0. Okay. So what about inner product xx? That's equal to, by definition, this is equal to quasi inner product of xx equal to inner product axx. This is greater than or equal to 0 because given a greater than or equal to 0. By definition, a greater than or equal to 0 implies inner product axx greater than or equal to 0. Now the second property ax1 plus bx2y, and this is equal to, by definition, this is a into ax1 plus bx2 comma y, and apply linearity property and then linearity of inner product, and we get ax1y plus bax2y, that's equal to aax1 plus ax1y plus bax2y, and this is quasi inner product x1y and this is quasi inner product of x2y. So what we get, this is equal to this one. Now in a product xy conjugate equal to axy conjugate, but a is a symmetric operator, therefore axy is same as xay conjugate, and this is same as ayx, and this is inner quasi inner product yx. That means this is a quasi inner product. Replacing xy by axy, we get, this is our star. Okay, here we are replacing this by a inner product axy. So this is inner product axx and this is inner product ayy. So we get this one. And this is our third property. Inner product axy less than or equal to root of inner product axx into root of inner product ayy. Now next one is fourth property. If C is symmetric A less than or equal to B, then A plus C less than or equal to B plus C. Okay. If C is symmetric and A less than or equal to B implies A plus C less than or equal to B plus C. We have A less than or equal to B implies clearly A and B are symmetric and B minus A greater than or equal to 0. Okay. So A less than or equal to B implies we have AXX inner product AXX less than or equal to BX inner product BXX. Okay. So to prove A plus C less than or equal to B plus C, what we have to prove? What we have to prove? A plus C less than or equal to B plus C. It is enough to prove that inner product A plus C XX less than or equal to inner product B plus C XX. Okay. Or you can use another method also. So we have A and B. Suppose A and C are symmetric, then A plus C is symmetric. Why? A to prove A plus C is symmetric, but we have to prove A plus C xy equal to x into A plus cy. Okay. So from here we get this one, and A and C are symmetric, we can write like this, and this implies x a plus a. So if A and C are symmetric, A plus C is symmetric, similarly B plus C is symmetric. So to prove A plus C less than or equal to B plus C, it is enough to prove that both A plus C and B plus C are symmetric, and B plus C minus A plus C greater than or equal to 0. So here B plus C minus A plus C greater C is equal to C, you can cancel B minus A, which is greater than or equal to 0, because A less than or equal to B implies B minus A greater than or equal to 0. From this, B plus C minus A plus C greater than or equal to 0. This implies A plus C less than or equal to B plus C. You can use this result, or there is one more. I'm not in this. We have A less than or equal to B means AXX less than or equal to BXX. And if we add some CXX, as this condition holds, some A less than or equal to B, these are in real numbers or complex numbers. So in complex numbers or real numbers, order property holds. Therefore, A less than or equal to B and C is some any real or complex numbers, then A plus C is clearly less than or equal to B plus C. So we are using this result here. Okay. And from this is same as A plus C x x less than or equal to B plus C x x. Okay. So we have AXX less than or equal to BXX implies A less than or equal to B. That implies from this we have A plus C less than or equal to B plus C. Okay. Now the last property, if A is symmetric, then A raised to 2n is greater than or equal to 0. So to prove A raised to 2n is greater than or equal to 0, it is enough to prove that inner product of A raised to 2n x greater than or equal to 0. Okay. So now moving to inner product A raised to 2n x. And this is equal to A of inner product A of A raised to 2n minus 1 x. But A is a symmetric operator, that implies A 2 raised to n minus 1 x ax. Inner product as symmetric implies inner product axy is same as xay. Okay, you take this as x, then this become xy. Some you can write az y equal to z. Sorry, this is zay. So you take this as some z. Okay, this implies zay. Now in the next step, this you can a raised to 2n minus 1, you can write as a raised to 2n minus 2x ax. And by again symmetry property, you take this as some z. So az and this as some y. This is set ay. That means this set into a of ax. That means a square x. Proceeding like this, here 2n minus 2, here 2. Here 2n minus 1, here 1. So here 2a, in the next step a raised to 2n minus 3 x is a x cube x. Proceeding like this, when this become n, total term become n, here also n. That means in a product a raised to nx, a raised to nx, and this is norm of a raised to nx whole square, and clearly that is greater than or equal to 0. Thus we get inner product a raised to 2nx x greater than or equal to 0, which implies a raised to 2n greater than or equal to 0. Now next, if a greater than or equal to 0, then a raised to 2n plus 1 is also greater than or equal to 0. So a greater than or equal to 0, a raised to 2n plus 1x x equal to a of a raised to 2nx x, and this is a raised to 2nx ax by again property, you can by symmetry property. Okay, so this is again repeating, and finally we get a raised to 2nx, a raised to 2nx. That is, this is of the form inner product ax x, or inner product az z, where z is equal to a raised to nx. Okay, so if you put z is equal to a raised to nx, this become a z z. But this is greater than or equal to 0, because given a greater than or equal to 0, in a product axx greater than or equal to 0. This implies a raised to 2n plus 1 greater than or equal to 0. And in the last term sentence is, if a greater than or equal to 0, then any polynomial p of lambda with non-negative coefficients, we have p of a greater than or equal to 0. Okay. So from above we get if a greater than or equal to 0, then a raised to 2n greater than or equal to 0 and a raised to 2n plus 1 greater than or equal to 0. Suppose p of lambda is any polynomial like degree n, and here we have given all ai are non-negative. Okay, that is ai is greater than or equal to 0. So what about p of a? P of a is actually a naught into I plus a1 a plus etc plus an a raised to n. Okay, we have a raised to n 2n greater than or equal to 0. This implies we have this one and we have this one for every n. And if you put n equal to 1, this become axx greater than or n equal to 2, we get a square x greater than or xx greater than. N equal to 3, we have inner product x cube x xx greater than or equal to 0. So what about inner product of P of A x x? This is like this. Okay. And this is equal to this one. And if you use linearity property, this is A naught Ix plus A1 Axx plus A2 A square x x etc. And here you can take constant outside. Okay, but we know that all these terms are 0 and all coefficients are greater than or equal to 0. Therefore, this is greater than or equal to 0. This implies inner product of PAX x greater than or equal to 0. This implies by order relation PA greater than or equal to 0. Okay, hope everything is clear. Just to recall what we have discussed today. So we have first definition. An operator A is called a non-negative. We write A greater than or equal to 0 if inner product AXX greater than or equal to 0 for all x belongs to H. Okay. And we have our next property minus I less than or equal to A less than or equal to I implies norm of A less than or equal to 1. And the next property minus I A less than or equal to A less than or equal to I into norm of A. Okay, minus I into norm of A less than or equal to A less than or equal to I into norm of A. Now the next, the inequality is A greater than or equal to 0 and A less than or equal to 0 implies A equal to 0. Next, generalized Cauchy-Schwarz inequality, let A greater than 0, then this condition holds. And the fourth property, if C is symmetric, A less than or equal to B, then A plus C less than or equal to B plus C. Next, if A is symmetric, then A raised to 2n is greater than or equal to 0. If A greater than or equal to 0, then A raised to 2n plus 1 greater than or equal to 0. And finally, if A greater than or equal to 0, then P of A greater than or equal to 0. That's all for today's class. Okay.